Welcome to the lecture 25 of Physics 10 in 30 lectures. In this lecture, we wrap up our coverage of quantum mechanics, which prepares for our remaining coverage of modern physics topics in the next 2 weeks. The main topic of importance here are the models of the atom, in particular the Bohr model of the hydrogen atom, as the first quantitatively successful model of the hydrogen atom that explained the features observed in the line spectra of hydrogen. After covering the Bohr model with a mix of old Physics 10 lecture video and borrowed Physics 4C lecture clip, the remaining lectures here reinforce the conceptual foundation of quantum mechanics and illustrate interesting applications. Quantum assumptions lecture is a borrowed conceptual lecture from Physics 4C, emphasizing three of the key relationships we have covered so far as the fundamental quantum assumptions that you will continue to see hold in fuller treatment of quantum mechanics. QM wave simulations covers the mathematical reason behind the uncertainty principle introduced in the last lecture set. And the lecture on lasers is just some extra material that we can now talk about with the knowledge of photons and discrete energy levels in an atom. Finally, we finish this lecture set with some homework questions from the quantum mechanics chapter, especially those that involve calculations and dealing with the scientific notation. As before, lectures that are borrowed from Physics 4C will make use of sections and snippets from OpenStax University Physics Volume 3, the textbook for Physics 4C. And the older lecture videos for Physics 10 show the shift in chapter numbers. That is, when you see Chapter 13 Quantum Mechanics, that is the same as our Chapter 12 on Quantum Mechanics, hosted on the LibriText platform. Now, we start with the models of the hydrogen atom. So I guess what I want to illustrate in the remaining 30 minutes or so is the historical aspect that I was alluding to in the discovery of atomic nucleus and Bohr's theory of hydrogen atom. There's two wonderful simulations on the PHYS website, which I think will be great illustrating this. I think one of these two simulations are new. So I actually haven't seen it before. We'll see how that goes. It's the Rutherford scattering. This is really the experiment that established existence of atomic nucleus, which led into the Bohr model. So yeah, let me use this simulation to briefly describe Rutherford experiment, which is described in the chapter section 13.5. So you can take a look at that too. If you prefer to read, it's all here, discovery of beta ray electron, and then the discovery of nucleus. Here's the figures and the written description. Let me use that simulation to what Rutherford was doing. Let me start out with the plum pudding atom, because this is the model that Rutherford was trying to he actually didn't believe in this model, and he was setting out to disprove this model. So you can kind of imagine this as a model of the, well, let's say it's gold, gold atom. So gold atom, from the studies that were done previously, people knew that it has a lot of electrons in it. That's what these small dots represent, electrons. And because we know gold atom to be electrically neutral, if it contains electrons, it must contain positive charges. And what plum pudding model has is it has this positive charge distributed in a uniform kind of way over the sides of the atom, so that these electrons can be embedded into it in a stable way. So Rutherford realized that he can use a radioactive phenomena that he's been working with for a while called alpha decay, which we'll get to in chapter 15. He realized that he could use that as an experimental tool to probe, literally, figuratively, no, literally, probe into this atom. Literally, in the sense that these alpha particles, which we'll later learn is the helium-4 nucleus, has enough energy to penetrate through this matter. So this is the schematic representation of the experiment. Rutherford has a source of alpha particle. He has a kind of atomic target that's spread out as thin as possible. That's why he chose gold, because it's possible to spread out gold foil super thin. And he kind of fired this alpha particle. He had the detectors all around to detect those alpha particles. Let's see what happens when we fire it. Wait. I can't do this one at a time. That's a super... all right, well, so that's what you would expect to see. Can I do traces? Yeah. So because these alpha particles have so much energy, let me see what happens if I try to have super low energy. Yeah, I guess, yeah, so most of the alpha sources have alpha particle with so much energy that basically all of them would be expected to go through mostly undeflected. This it's like, you know, imagine shooting bullet through air. That's basically what this is, or I guess bullet through tissue paper. That's what you would expect to see. And what Rutherford was hoping to see was, he was hoping to not see this. And he was right, he did not see this. That's why he had the detectors all around, hoping to detect deflections. Now, what it did see was nonetheless surprising. So, so let me, without going too far into this, let me just show what Rutherford. Yeah, let me see what this does. I guess we could do that. I think this is a little bit too busy. There's too much things going on. Let me imagine just focusing on a single atom here. That's what the second option is. So you will have to kind of ignore what you see at the center. Let me turn on the traces that will help you see what Rutherford was seeing. So, so a big part of what Rutherford was seeing is actually better represented here? So, well, maybe a little bit. Okay, it's a bit exaggerated. So you see some of these particles that are going through mostly undeflected. And that actually makes up a vast majority of the alpha particles. So for the detector that's positioned here, you know, it detects most of the alpha particles. So that, all right, that's there. What Rutherford was seeing and what led him to posit this model that you see represented here are these large deflections. So that's what Rutherford is quoted as saying, it's as if you shot a, I don't know, 20 caliber bullet and at a tissue paper, and it came back and hit you. You see in these schematic representations, these alpha particles, depending on how close they are to the head-on collision, they go through different amounts of deflection. And the thing that was very surprising to Rutherford was that you had these alpha particles that have basically come to a complete stop and deflected through a very large angle. And for that to be possible, he had to modify from this plum pudding atom, which had most of the mass of the atom and the positive charge spread out over a large area, into very compact, very small area. And I keep saying this is kind of exaggerated scale this is exaggerated scale, because if this diameter is meant to reflect the size of an atom, 10 to minus 10 meters, then this size of the nucleus should really be 10 to minus 14, 10,000 times smaller by radius. So, so that's how small the atomic nucleus had to be to fit with the experimental observation. So that's the discovery of atomic nucleus. It comes from this experiment that what's Rutherford's first name? Well, Rutherford did, and then he figured out this is the only model, one that puts all the masses of the atom in a very tight, confined space, is what's able to describe the experimental results that he saw. Now, once you do that, then you have a bit of a dilemma or problem. The motivation for this plum pudding model was really to have an electrostatically stable configuration of electrons and protons. That's what the motivation here was. But experiment is saying that's not realistic, that's not possible. Then what other model is there? That's what this simulation is exploring, models of a hydrogen atom. I think I actually used this simulation earlier when we were talking about scientific models. So if you remember that from the first week of the semester, great. Now that we are here, where we are actually talking about quantum mechanics, I can actually just run through what the different predictions due to different models are. And that's what this section 13.6 is getting at. It gets at Bohr's, so 13.6 describes Bohr's theory of a hydrogen atom, which is the model that won out over other possible models. And let me, to give this model a context, let me give you the description of the other models of hydrogen atom. So the simplest model of hydrogen atom is kind of the Greek, as in ancient Greece, Greek imagination of the atom, and kind of indivisible particle of matter. And if that's the case, then when you fire, so all these particles represent photon, light, they will all kind of reflect in the same way, regardless of wavelength. And experiments show both in many different ways that that's just not the case. How light bounces off of matter depends on wavelength. That's why you see different colors. That's why, so billiard-ball model fails. For that reason. Also, it's kind of Greek philosophy, not modern physics. And plum pudding model would give a similar explanation, but through classical physics, as in this incoming wave of electromagnetic wave would shake the electrons inside an atom, and that electron would re-emit the light. And this dependence might have some dependence on wavelength, but not very strong. But I don't know why it's building up that way. Yeah. But plum pudding model, we also reject that for a different reason, the Rutherford experiment. Then, so the remainder of the models start out with the conclusion of Rutherford's experiment as the starting point, that there is an atomic nucleus that contains almost all the mass of the atom, all the mass of the positive charge, and you still have to have somehow stable configuration of the positive charge and the negative charge that still adds up to the size of the atom. And physicists drew inspiration from nature. They try to look at, okay, what other thing has kind of relatively compact particles that make up a larger system, and they realized our solar system It's kind of like that. So this is what classical solar system represents. And a lot of people worked on their model. And this is what this model would end up predicting. It's a bit of fun, but what happened? Okay, let me stop the simulation. So, okay, I paused the simulation. So when you, let me make the simulation super slow. When you start the simulation, this is what you are seeing. So you have a proton, that's the atomic nucleus for the hydrogen atom. And you have electron that's going to be in orbit. And it just ends up losing orbit super quickly. And the reason for this is it's the theory of electromagnetism. We talked about in chapter 12 how oscillating charge produces electromagnetic wave. This electron that's orbiting proton, that's an oscillating charge. And that oscillating charge has to emit electromagnetic wave. Electromagnetic waves carry away energy. And if this electron is losing energy, then it must spiral into the proton, almost like a satellite around the Earth that's losing orbit because it's losing energy due to friction. It crashes into Earth. So electron has to do something like that. So this classical solar system model of hydrogen atom gives you basically absurd prediction that hydrogen atoms won't be stable, which is once again absurd. That's not true. So, so that's what baffled scientists until Bohr came up with his model, where he kind of posited these stable orbits of electrons, and these stable orbits basically come from the assumption that the angular momentum of these electrons are. So this is where the science of spectroscopy is actually helpful. And let me show you the spectrum so that you have a background for what I'm talking about. Let me pass out this diffraction grating. Let me show you the hydrogen spectrum. If you would take one and pass the rest around, while it goes around, let me set up the hydrogen tube here, so that you can see what the hydrogen spectrum looks like. And so, you know, it's kind of easy to come up with a theory that says your atom should be stable. That seems like that's not a high bar to clear. But what's a more difficult bar to clear is explaining something more quantitative. Not merely the fact that your atoms don't implode, which is an absurd result for a theory to predict in the first place, but you have some experimental phenomenon that you see with atoms that now the goal is to explain why do we see that. So, so this is the hydrogen tube. People have been playing with this for a while. When you turn it on, it produces this light, magenta light. People have seen that for a long time. By the way, I kind of have to, I can't leave this on for a long time. I'm going to turn it off so that I have a little time to explain what I want you to do. So take this diffraction grating, hold it horizontally right in front of your eye. When I turn this on, look at it directly. You will just see the magenta light. But as you're looking at it directly, look to your left or right. Then you will see the line spectrum that's spread out. Okay, I can turn it on for 30 seconds and then I'll have to turn it off again. So look, so those line spectrum, and everyone sees those line spectrum? What colors do you see? You see red and green. Do you see blue? Yeah, like a cyan or, oh, I guess what you're calling green is actually probably cyan. And there's a more deeper blue there, right? So, that's the spectrum of a hydrogen. And measuring that is the science of spectroscopy, and people have been measuring that for a very long time. And that leads to a kind of predictions. It leads to the prediction of, well, if an atom has a particular structure, then the atom is going to interact with the light in such a way that it emits those specific wavelengths of light.
What we are going to look at now is the Bohr model. This is the model that led to the correct prediction of energies, which leads to the correct prediction of frequencies, which leads to the correct prediction of the wavelengths that you are seeing. So this is kind of a starting place for the Bohr model. And so I will sketch the model, and then I will point out what the quantum mechanical ad hoc assumption he's making is. So this is the Bohr model of hydrogen. So he actually starts from this solar system model. So you start out with, all right, I'm going to have the atomic nucleus that has all of the positive charge at the very center. This is what we'll end up calling proton. So, all right, you have the proton here. And the electron is going to be in orbit around this proton. So you have electron that's in orbit around the proton. If that's all you have, then you get the same absurd result before. So Bohr has to put in one more assumption on top of this to avoid this result. And this is a strange assumption that he's making. So this is Bohr's assumption. Quantum mechanical assumption. And it goes without saying it's an ad hoc assumption. If you asked him for, why do you think that's true? His answer would be, well, it gives me correct prediction. Actually, correct quote-unquote prediction, because it's not really a prediction. It's just reproducing what you already see experimentally. And in fact, this is such a strange idea that there were some physicists, Stern and Gerlach, that set out to test this idea. And what they said to each other was that if Bohr's idea turned out to be correct, they will quit physics. They didn't actually quit physics, but it was strange enough that it's not something that came to people naturally. So this is his assumption. He's saying, all right, this electron, it's in orbit, it has mass, so it has an angular momentum, right? So he said, angular momentum, let me assign a letter, L, of electron comes in discrete quantities. That's the assumption he made. And once you make that assumption, you kind of look at how you can discretize this angular momentum. And this is not the first time somebody said this quantity that we used to treat as continuous can take any value, comes in units of something. I mean, it's right there. So the first time somebody tried to quantize it this way, they used this Planck's constant. Well, Planck did it, and we now call it Planck's constant. So this discretization of angular momentum is done on a similar basis. I'm going to write down an expression which won't really be intuitive, but we'll get to it later. So mathematically, you would say this. This angular momentum, it comes in integer units, so of n. So this is integer. It comes in integer units of this, n times Planck's constant divided by 2 pi. Sorry, there's a 2 pi in there for some reason. So actually, this particular combination of constants happen a lot in quantum mechanics. So kind of like with the gamma in special relativity, we give this a special letter. It's called h bar. Or if you want to spell it out, Mathematica calls this reduced Planck constant. So in terms of this, this is what Bohr assumed, that angular momentum of this electron comes in these discrete quantities, n, h bar. So I guess Bohr was somehow assuming that, so with this model in mind, could you have this angular momentum to be 0? Now, if you are a chemistry major, you might know something from chemistry that, in the s orbital, electron has 0 angular momentum. I want you to forget about that for the time being. in this particular physical model we are building, is n equals 0 a possibility? It's not. This is one aspect of Bohr's model that is actually wrong. So Bohr's model is not the correct quantum mechanics. It's a stepping stone to the correct quantum mechanic. So that'll be the one thing about Bohr's model that's not quite right. So what's the smallest number you could have for n? You want to put something in orbit. We said this can only be an integer. 1 is the smallest number it can be, right? If it's 0, it's out of the question. Yeah, so that would be the smallest value n can be. And for the chemistry majors here, we actually retain this notation. In chemistry, this is what you call principal quantum number. And when you look at the periodic table, this is the n. 1, 2, 3, 4, 5, 6, 7. Now, the little part that Bohr got wrong was that you could have n equals 1 and the angular momentum be equal to 0. So we'll get to that, but I want to just show you that this plus what you know in classical mechanics leads to the correct result. So this is really, this is what we want to derive. We want to derive an expression for energies of this electron. So we want to say, when this electron is in one particular orbit with n equals 1, we want to be able to say this has energy E1, right? And we want to say if it's on some different orbit with n equals 2, we want to say it has energy E2. And if it's on an even larger orbit, then you keep going with that. On a larger, it's not drawn to scale, by the way. On this larger orbit with n equals 3, we want to say it has energy E3. And this is really what we, to compare this against this prediction in, quote unquote, prediction in spectroscopy you have seen, this is what we want to be able to say. We want to be able to say the difference between these energy levels. For example, E3 minus E2 gives you, so, as electron goes from here and somehow goes down into this lower level, as it's doing that, it's going to emit a photon. It's going to emit photon or light as it's doing that. And we want to say that this difference in the energy levels of the electron is where the energy of the photon, h times frequency of, I don't know, hydrogen spectrum, comes from. Yeah? So the starting place here is that we need to derive an expression for the energy of the electron as a function of this parameter n. So that'll take a little bit of time. We have to review some classical mechanics and go through not that complicated of an algebra. Did I do everything else correctly? Yes. So this is the quantum mechanical piece that we are inserting into everything that we have been doing so far that has been classical. We are saying, all right, this expression for r, this is my quantized orbital radius. This r is a function of n. Everything else here is a constant. So what we are saying is, well, only the radius where n is equal to 1, 2, 3, 4, those are the only allowed radius for the electron. That's our quantum mechanical assumption. It's a very strange assumption. Once again, there are a lot of physicists around Bohr's time who thought this was a crazy idea. But, well, once you're exploring what is the consequence of this crazy idea. And, well, so this is one of the consequences. I happen to have energy already expressed in terms of radius r. So let's see what this energy is in terms of all these other things. So I want to plug in this Rn, or rather 1 over Rn, right? So that's what I'm plugging in. So it's E squared m divided by 4 pi epsilon naught, skip n for now, h bar squared. So that's, and then I'll have this n squared, so 1 over n squared. That's 1 over r so far, right? Times, and I'm going to write in all the quantities that's coming from all these constants. I have minus, that's coming from there. And then I'm having divided by 4 pi epsilon naught. Okay, so it's going to be this 4 pi epsilon naught squared. Yeah. I have e squared. So this e taken to power of 4 now. And then divided by 2. So 1/2. So this is what it comes down to. We are saying this energy, which we are now going to say is quantized energy. Energy as a function of n is this collection of constants times 1 over n squared. So I guess here's another way to put it. We can say that this En is, we can say that it's minus E naught, where E naught is all this collection of constants divided by n squared. And I happen to have the number E naught memorized. When you plug in all these constants, I will write it down, and then let's just show you the Wolfram alpha. This E naught, it turns out to be a pretty simple, easy to memorize number. So it does come in units of energy, and this E naught is 13.6 electron volts. As long as you memorize in electron volts, it's such a nice round number. Let's just confirm that I remembered it correctly. Wolfram alpha. All right, I have to plug in all those right. So I'm skipping minus for now. Elementary charge squared, to the 4th power times. That m is electron mass. Electron mass divided by 2 times 4 times pi times electric constant squared times, and that h bar is called the reduced Planck constant. Reduced Planck constant squared. I can actually simplify that a little bit, but I chose not to. Is that everything? Guess that is. Let's type enter and just confirm when the screen comes up that it's the correct full expression. So let's see, e to the 4th power times me divided by 2 4 pi epsilon naught squared h bar squared. All right. There it is. In electron volts, it's a 13.6. Nice. I guess it's not exactly round. Nice round number to memorize. So this is, but this is really the key feature that we are looking for. That is verified by experiment. This energy levels. So going back to this, the energy levels. So these are the allowed orbits. So this would be 1, 2, 3, 4th orbit. This is so the energy that it has at the 4th orbit, and the light that's coming from this hydrogen atom, you would say is coming from when this electron is falling from here to some other level. So if it's going from the 4th orbit to the 2nd orbit, you would say that the energy of the photon, or h times frequency, is coming from this difference in energy, E4 minus E2. And when you work out the numbers for this, you should get that cyan wavelength. So this is the picture you have seen, right? This is the spectrum of a hydrogen atom you have seen. And people have studied this for a long time, and people have studied this spacing of wavelengths for a long time. And there was an even experimental law that said that when you calculate the frequencies, or I guess you can put it this way, that this 1 over wavelength was always, you could kind of write it out this way. That's equal to something called Rydberg constant times the difference in the reciprocal of two integers. 1 over m minus 1 over n, or the other way around, I forget. This is some law that a guy named Rydberg figured out. It's, without any underlying theory or kind of theoretical derivation, they figured that out from experiment, sort of like a Planck law. And what we now have is a theoretical explanation for this. Sorry, forgot, squared. What we now have is a theoretical explanation for this. This is true because the electron energies in hydrogen goes as 1 over n squared, where this is an integer.
That they are quantized, and that's what these stable orbits represent. And the experimental results that people get with that, which is the spectrum of the hydrogen atom, matches with the predictions that Bohr model produces. Well, quote unquote prediction, because he already knew what would be. And so that's really the reason people were accepting the Bohr model, that it gave a result that agreed with the experiments. And with the de Broglie wavelength hypothesis, you can kind of expand this model a little bit. Think of each of these stable orbits as representing a standing wave of electron, which, depending on your point of view, may be better grounded. And I was saying earlier how even this is not really the correct, fully correct picture of hydrogen atom. That we don't actually think about electron orbits in this way. This Schrödinger model is that's the fully correct model. In chemistry, you might have heard of electron clouds. That's what this is representing. And it's difficult to talk about this electron cloud in a way that's not incorrect without super complicated math. So I won't do that. Only to say that when chemists tell you about electron orbitals and show you pretty pictures that look like that, believe them. That's our modern understanding of hydrogen atom. I'll just leave that there. So I think that's all the time I have. I hope this is somehow useful to you in getting started on really the set of topics that I was in a hurry to get to. This is the interesting aspect of physics. This is where I hope you will, this is where I hope if you weren't already interested in physics, that you will get interested in physics. And for many of you who are in allied health, chapter 15 is where it'll get super interesting because there's like medical imaging and diagnosis. I think that's really the reason your program requires physics. So at this point in our coverage of quantum mechanics, I think it's good to spell out and enumerate what I'm going to be calling quantum assumptions. As I say in a few places, quantum mechanics has pragmatic beginning. So a lot of the development of quantum mechanics kind of has this feel of someone trying to figure out the layout of the room in a completely dark setting just by feeling around. And the beginning of quantum mechanics begins with a few ad hoc assumptions. And what I want to highlight here are some key assumptions that turn out to be lasting, turn out to be incorporated into the the fully built out model of quantum mechanics. And the first of those assumptions are introduced by Max Planck. It was introduced as he was trying to develop what we call Planck law that explains the black body radiation spectrum. And he introduced this assumption that the energy of an oscillator can have only discrete quantized values. Let me write it in a slightly different way, which goes a little bit better with the format that Einstein used in his explanation of the photoelectric effect, which is that there's this relationship between energy and frequency of oscillatory phenomena, that the quantized energy of an oscillatory phenomena is proportional to its frequency, and the constant of proportionality, uh, letter H, which we call Planck's constant, it's fundamental that there are several different phenomena where you can really only fully explain it by assuming a quantized discrete amount of energy transferring, and this is the unit of that quantized energy. And Einstein extended this idea of Max Planck's to posit existence of photons, particle of light, that he used to explain photoelectric effect. And I talked about how Einstein actually didn't go far enough. The other key assumption that turns out to hold as we later introduce wave mechanics is de Broglie hypothesis. De Broglie's supposition that this relationship between light wave and photon might hold for everything that has momentum. I'm going to write this in a slightly different way, which would be to relate momentum of something like light or a particle, that it's going to be related to its wavelength by Planck's constant divided by wavelength. So this is the de Broglie hypothesis, and this is a kind of a natural consequence of what Einstein assumed about photon. And the kind of surprising thing is that this turns out to hold for everything. And your textbook talks about wave-particle duality, and yeah, and this expression relates to both what we typically associate with a particle property, that is momentum, with the wave property, that is wavelength. And I want to, in this short lecture, I want to introduce us to one more quantum assumption that you're going to see later this week. And this is going to turn out to be fundamentally important in many different areas. And I guess in the context of this class, you will see its role in chapter 8 as we talk about the atomic levels and all that. The place where this assumption gets introduced is in the Bohr's semi-classical model of the hydrogen atom. So let me scroll to the place where Bohr's assumption comes in. And, when we talk about the Bohr model, we do say that it's not fully correct. There are some things that Bohr got wrong. But the one thing that will turn out to be correct to a far greater extent than Bohr might even have guessed is this idea of quantization of angular momentum. So the idea that angular momentum comes in this quantized unit of h bar, reduced to Planck constant, where it's a shorthand that we use for h divided by 2 pi. It saves us a lot of writing by not having to write 2 pi every single time. The idea of quantization of angular momentum, it's going to hold for orbital angular momentum, which is what Bohr was considering in his model of a hydrogen atom. And it's going to hold for other kinds of angular momentum, like the spin angular momentum, that you will see more of in chapter 8 later on. So, so these are what I like to highlight as quantum assumptions, because as we introduce quantum mechanics in a semi-historical fashion, some of the things we introduce are not the things that will ultimately turn out to be fully correct, like the Bohr's model. That's not the fully correct model of the hydrogen atom as we understand it. But these assumptions are the things that as we will turn out, we won't have to change any of these as you learn quantum mechanics better. We'll be able to retain these, fold these into our mathematics of quantum mechanics. So watch out for them as we continue our study in quantum mechanics and physics in general. Let me go through something that's a bit extracurricular, but I think it'll help explain some of the things that I think I don't quite fully explain, that I'd like to explain a little bit more fully. Um, One of them that I think I'm realizing as I'm going through this session is the natural connection between uncertainty in momentum and uncertainty in position. And that is best illustrated with this simulation. So the connection there, it's quite mathematical connection. So that's why I don't want to dwell on it too much. It's a mathematical process called the Fourier analysis that it gives the explanation of this. Um, so does the quick description of Fourier analysis. It's a way of representing any arbitrary repeating function in terms of components of a sinusoidal oscillating function. So here, I have a sine function that I'm trying to illustrate, and yeah, okay, it can be illustrated by a sine function. And if you imagine adding multiple sine functions, so each of these are sinusoidal of different frequency, what we call harmonic. Then you get some shape here so this is what you get when you add all this together, and you're beginning to see a shape that looks quite different from just regular sinusoidal. And this kind of Fourier decomposition can be used to actually analyze any kind of arbitrary function. So this simulation has some presets, like what if you have a triangular wave? Then a triangular wave can be expressed as this one sine function that already kind of matches the triangular shape. And to develop this sharp corner, you add these. So nothing here, but okay, this one, you see that highlighted yellow, nothing here. But okay, so these higher harmonics are actually quite small. So let me show you something where you will see greater influence of those higher harmonics. Let me try a square. So square wave involves this sharp transition, or what's attempted as the sharp transition. So in order to get this sharp transition, you have to add these significant parts of the higher harmonic. And the sharpness of this transition is limited by the highest frequency that's included here. In the limit where this goes to infinity, I can approximate square wave to the arbitrary precision. Wonder what it says under wave packet. Oh, I think that's the fun one. Does that? Well, okay. I mean, I don't know how much I like this. I don't like this too much. So let me show you that connection between uncertainty in momentum and in uncertainty in position. I think there's one thing that you can see here is that with all these things you're adding up here, the the total wave that you see here, it's what you might call localized. It's localized within this space here. You have negligible amplitudes out here. And there's a reason. The way these waves are added, you see that within this region, all these different waves, they add constructively. where one wave is increasing, all the other waves are kind of increasing as well. So you see this constructive sum here, and the same on here. And as you go farther out, you kind of see this more random looking thing. And that's where all these different components add destructively. That's why you see more or less a flat line here. And in this, I think a discrete to continuous step is where you can really see how in an attempt to localize a particle, localize the wave packet, you must introduce uncertainty in wavelength. So let me show you here. So here, this is some preset thing, and this is my wave packet. And the way set this up, they have it repeating. It repeats every whatever this interval shown. But you can just pretend that we are focusing on this one portion here. So the simulation has two parameters that lets me control how the wave packet appears. It gives me this wave packet width parameter. It has width in terms of position. That's so small, but that's what this sigma x is. It has this width in terms of what they call k, or wave number. You can think of it as the inverse of the wavelength. Well, there's 2 pi there. That's why it's in radians per meter. But this per meter portion tells you that it's inversely proportional to the wavelength. So, so right now, this packet here, it has large width in terms of this k value, the wave number, inverse of wavelength value. So let's say, all right, I want more precise wave number. So let me make this width smaller. So as I make this width smaller, I hope you notice something. So up here, this graph, so compared to where I had a larger width, this narrower width graph has fewer values of wave components. So this is the carrier wave, or the center frequency, and these side bands are what allows you to modulate your amplitude of the wave. And as I make the packet width in terms of wave number narrower, resulting in more precise wavelengths, you see that my wave packet is more and more spread out. In fact, in the limit where my wave is very well defined in terms of wavelength, there's only one way that such a well-defined wavelength can correspond to the waveform in space. It has to be all in all space, because it's basically one sine function that's spread all over. So by decreasing the uncertainty in wave number, or uncertainty in wavelength, I've had to increase the uncertainty in position. And all of this is, by the way, just classical wave theory. If we are willing to deal with all the mathematics of it, then we can do that. Just, Fourier analysis, it's all math. The quantum mechanical piece comes in when you associate the wavelength, or this wave number, to the momentum, the de Broglie relationship. The Planck's constant is equal to momentum divided by wavelength, or the Planck's sorry, I don't know how to say this out loud. Let me write it down. The de Broglie relationship, which relates momentum to wavelength. I guess let me put it that way, or wavelength to momentum. I think this is the version that's in your textbook. Momentum is given by Planck's constant divided by wavelength. This relates the wavelength, which is what the simulation is dealing with, to momentum, which is a particle property. So through this relationship, any uncertainty in wavelength becomes uncertainty in momentum. And that's where the natural connection between, that's where you get to the Heisenberg uncertainty principle, that this is the natural connection between the uncertainty in position and uncertainty in wavelength. And through this relationship, uncertainty in wavelength becomes uncertainty in momentum. So, so this idea is quite a bit mathematical, which is I didn't want to talk about it too much, but you can at least play with the simulation and look at different things and look at pretty pictures. Let me just show you one more simulation to kind of wrap this up. Oh, I don't have a lot of time. So this is the simulation that I linked in the announcement, and I just wanted to show you a representation of quantum state. This is the kind of what representation of quantum state looks like. Let's see, what can I say here that's not super mathematical? Well, I think I can show you some aspects of this, which is, so quantum tunneling, I don't think we are really covering it all that much, so let me skip that part. I think one thing I can show you is, so I think this line here, that's the average energy. So the average energy, and the distance between this line and this potential energy represents the kinetic energy. So the larger the distance here means the larger kinetic energy the particle would have, and larger kinetic energy means larger momentum. And you can kind of see it here, how larger momentum means shorter wavelength, and smaller momentum means you can't really see much of a wavelength because it's just one bump. So let me actually do this. I'm gonna make the width of my wave packet larger. When I do that, you see this. So with a larger width of wave packet, you see that, okay, now I actually have enough space to actually illustrate that wavelength thing I was referring to. You see how curved this is doesn't really change with the width. All that the width changes is, hey, with this much curving, do I have enough space to show the oscillation? And I want you to see this. This green bar, the whole smearing of the bar, it represents the uncertainty in the energy of the particle. And you see that the less certain we are about the position of the particle, the more certain we become of its momentum and hence its kinetic energy. So that's one that you can kind of see here. And yeah, this particle is moving across super slow because I set it up so that it has a very small kinetic energy. Yeah. So that's one. And you can see this uncertainty momentum aspect through this part of the simulation. You see how as this wide bump moves across, nothing really changes. It's wide bump that's moving across. Now, when I return this to the, not all settings, when I return this to the width that it was around, then you will see something change a little bit. So with this more highly localized particle, watch what happens as it moves across. You see it spreading out. And there's a reason for that. It spreads out because here it's simulating an electron. So it's a particle with a mass. And so its momentum is related to its velocity by mass times velocity. That's the momentum. So when it had this well-defined within position, it had a rather significant uncertainty in momentum as represented by this spread in energy. So this uncertainty in momentum means uncertainty in velocity. And uncertainty in velocity means that certain parts of this wave, in some sense, part, quote unquote, moves faster and some parts move slower. And that different speeds of different parts of the particle makes it spread out. And finally, you can see an extreme version of that if I make a quantum measurement. And so this is the part where I guess I probably shouldn't get into because it's the aspect of quantum mechanics that's frankly confusing to a lot of people. And I don't have enough time either in this session or in the class as a whole to spend enough time with it to actually give it a proper treatment to what the Copenhagen interpretation of quantum mechanics says. I'll just say this part. So all this that you've seen so far is all deterministic. It's all reversible, deterministic time evolution of quantum state. What makes quantum mechanics so challenging conceptually, philosophically, is that when you make a measurement, there have to be a what's called stochastic collapse of wave function. As in, this wave function here, it represents all different possible places the particle can be. Now, when you make an actual measurement of particle position, it'll you measure the particle to be at one position. You don't see it all spread out if with a single particle. So this is what the simulation simulates. When you make a quantum measurement, the particle simulate to you detecting the particle at a single point, really limited by just the precision of your whatever instrument you are using. Now, when you detect a particle this way, you have highly localized the particle. And that detection process has to involve imparting large momentum uncertainty. This collapsed wave function, it has such large uncertainty momentum that when I let the time flow, some part of the particle is actually moving the other way from its original direction. Um, so, so yeah, and that stochastic it's a stochastic means random. So it's really random. That's what the simulation simulates. When I make a quantum measurement, it randomly, with some chances that that's proportional to this, shows the particle here. But when I reset and remake the measurement, I'm not guaranteed to find the particle in the same spot. The only thing that the theory tells me is that I have a significant chance of finding the particle somewhere in this range. I have close to 0% chance of finding the particle way out here. So, um, so yeah, that's all I wanted to demonstrate. And I think this is a good place to leave our discussion of quantum mechanics, because I don't want to leave you with sense of feeling that not all of this makes perfect sense, which is perfectly fine, particularly for in modern physics. At the same time, I don't just to want to tell you that nothing is known. We don't know like that's not the case. We do understand quite a bit of quantum mechanics. It's just that it involves quite a bit of unintuitive concepts. They should have addressed this point about coherence, that for or lack of coherence could be a potentially limiting factor in whether you can observe interference effect or not. Let me see here, coherence. Yeah. So they do talk about coherence here, and, so there's some information there, and what I want you to do here is, so you see the word description here, and I think the kind of the downside of it here is that it's well. I wanted to give an alternate presentation where if this word description about coherence or incoherence makes sense, then great. Good. I guess what I'll do for the next 5 minutes or so, you don't really need it. If this didn't make immediate sense, then I want to kind of illustrate it. And this, by the way, also connects to the nature of unpolarized light. And as we are talking about interference, so that's where kind of the unpolarized light being unpolarized, that is one of the features of incoherent light, because when a light is unpolarized, the way it's unpolarized is each given kind of burst of light does have a given polarization, but it randomly shifts, and that random shift is what
results in the things that you observe with unpolarized light. So the demonstration that I thought would be useful for illustrating circumstances where you get coherence. I thought laser simulation would be great for illustrating that, because in fact the coherence is a special feature of laser light. Most light sources in the world is not coherent. In fact, there are very little things we can do to make natural light sources coherent. They come incoherent and they're just going to remain incoherent. It's with the lasers where you can actually produce coherent light. And it has to do with how laser operates. It's something that we unfortunately won't take a lot of time on. I think your textbook does have a chapter on lasers that, or section on lasers. I recommend that you read it. Wait, does it not have anything on lasers? Oh, wait, there it is. Yeah, lasers. So you can also talk about lasers when we talk about atomic structure, because that's the place where we would be equipped to talk about how you get the light amplification. So, so this is a simulation that what I want to show here is, let me start out with, I think I can do this with the multiple atoms. So let me shine some light. And here you can kind of see what the normal sources of light, or normal natural non-laser sources of light look like. It's let me start the simulation, pause it. So you see these atoms or models of atoms emitting light. They emit light when they undergo transitions. You know, the incident light, it excites these atoms from level 1 to level 3, and as they decay down to level 2, and as they decay from 2 to 1, that's when they emit light. And this light that these atoms are emitting, they are random. They um, so the this light that one atom emits doesn't really have any relationship with the this light that another atom emits. So this is where you get randomly shifting phases and randomly shifting polarization. That's the source of incoherence. It's things that are incoherent because they have no relationship to each other. And so they, so you wouldn't expect them to be related, and they are not related. And even for the lights that are heading the mostly the same way, let me see if I can capture some of that. It's kind of hard to capture here. Let me see if I can do that with a stronger light. So occasionally you might, like these two light particles, they're going mostly the same way, but they still have no relationship to do with each other. They are still not related to each other in terms of phase or in terms of polarization. That's the source of incoherence. That's where you get things that are just randomly distributed. And and when you have things, when you have that incoherence, that when you can see interference, because our ability to observe interference, it relies on there being a stable phase relationship that lasts for some appreciable amount of time or length of light transmission, so that because what we observe is always a time averaged quantity, and we need those interference patterns not to be washed out in the time average. So now laser is special in that it can produce coherent light. And you kind of see hint of that. I've been trying not to bring attention to it. This simulation is designed so that sometimes it shows these doubled light particles. And these two photons they are related to each other. They have the same phase, the same polarization. They are copies of each other. So laser is a device that's designed to amplify situations like this. So let me set just to change this simulation so that it'll show the lasing condition. To do that, I need a metastable state. and I need a mirror to kind of trap that in for a bit. Um, let's see. It's been a while since I played with the simulation, so I don't know the exact parameters that will work. Let me give this a little bit of a try. Um, oh, wait, I did this wrong. Lifetime for 2 should be long to be metal stable. Okay. Um, all right. Yeah, so I think I might need a better reflectivity. Okay. Yeah. Okay. So what you have here is what's called a population inversion in thermodynamics or statistical mechanics. It's normal for lower energy levels to have a more number of higher population. And in the laser setup, you invert the population with some either convenient arrangement or whatever, so that a state with a higher amount of energy actually has more population of atoms in that state. And when you have enough of this, you can get um, more of a, what's called a stimulated emission. So see if I can capture that. Okay, I think it's one of these two particles will hopefully hit either this or this atom before they decay. Then you will see stimulated emission taking place. Um, yeah, so this is just to hit that too. And I think, did that just appear with that? No, I think that just decayed on its own. Let me see if I can find the one there. I'm looking at this, hoping that this will get stimulated emission. No, I don't really necessarily know the details of. Okay, I'm just watching it, this one, seeing if this will get undergo stimulated emission by either one of these two. Um, no. Oh wait, there it is. Yeah, when that one photon hit this, it went down to level 1, and there were these two additional photons that came up. That's the phenomenon of stimulated emission. And when that happens, that's when you get light amplification. That's the LA of laser. And so the special feature here is that these two photons have the same characteristics, same phase, same polarization, same everything. So in a laser, you end up with a buildup with light that's basically um, light that's copies of each other. So that's where you can get coherence. These light that's being emitted out here, they have a stable phase relationship. So the light that's coming out at about the same location, they will have the same phase. That light that's out here, the phase difference from here to here will be predictable through the as a fraction of the wavelength. So so that's why when you see me doing interference demos in the lecture, you will always see me doing that with the laser, because it's just easier with the laser. And now you can do interference demos with normal sources of light. People have been doing interference experiments well before lasers were invented. But what they had to make sure it was, they had to make sure that their experimental setup was within the coherence length of the light source that they were using. Usually the longer lived states and narrower lines, they are associated with the longer coherence length. So so with this, you can do interference experiments with the sodium lens. You just have to take some precautions, take measures to ensure that that the kind of the experiment you are trying to set up is within the coherence limit of your light source. So that's why when we see when we present the double slit interference, we present it this way. It's a single slit here. Young needed that in order to make sure that his light source from this point on is more or less coherent. because it's such a small slit. It only lets a small portion of the light through, so that he could rely on some kind of a coherence relationship between light that's arriving here and here. So when we use the lasers, that avoids the need for this single slit, because when we have a coherent light to start with, then we can just have that and have it go through double slit. All right, so I'm going to skip all the multiple choice portions. Those are basically reading checks. You should read the book and get them right. I mean, you could, well, yeah. So let me just focus on the calculation parts. Now, even for the calculation questions, the hint tries to give you help where it's needed. A lot of times it'll say review the section, and it's mainly because the key formulas, key relationships you need to use, they are in the section. So it says read the photoelectric effect because the question is about energy of photon. And the section itself goes into what expression gives you energy of the photon. There it is. Energy of the photon is h, Planck's constant, times frequency. That's the key equation, key expression, key relationship you need to use. So that's why it says read the section. So assuming you've done that, let me write it down on the side for myself. The energy of the photon is equal to Planck's constant times frequency. And oh, well, there, it's also there. And Planck's constant is given here. And now you do need to recall from earlier wave chapters this relationship between the frequency and the wavelength. That's why I'm giving you that relationship. Because for some of these questions, you'll be given the wavelength instead of the frequency. So you have to be proficient in doing the calculation. So let's go ahead and do this calculation. So the first question, we are given the frequency of the radio wave. So just to spell it out, the frequency that's given there is the 80 megahertz. Or 80 times mega is the metric prefix, meaning 10 to the 6 or a million, 10 to the 6 hertz. So I have Planck's constant there. So all right, let me do this on a calculator. Yeah, let me. I think it's easier. Wolfram alpha is the easier way to do it. So I think you can do that for yourself. So let me demonstrate this on a calculator. For those of you who want to make sure that you know how to do this on your calculator. So this is a kind of a standard-ish layout for a calculator that should be relatively common, hopefully. So let me do H, 6.626, and power of 10. It's this button for this calculator. Oh wait, not that button, sorry. Oh, where's my, I think it's that one. Okay, let me do 6.626. This is the times 10 to the power of button. So 34 minus. So this is the Planck's constant in SI units, joule times a second, times this number here, 80 times 10 to the 6 hertz, 80 times 10 to the 6. Hertz is 1 over second, so that 1 over second will cancel out the unit of second here, giving me unit of joule. So equals, gets me that. Can I display that in? Oh, I know. So how do I explain this? So whatever number I have here, I don't actually want to plug in that number. I want to plug in the number without this power of 10 part times 10 to power of minus 25. So how do I express this? Let me express this number here. The number that's represented here. let me use just the letter, I don't know, X to represent this number. What I want to plug in here isn't actually the X. Let me call this Y. The relationship between X and Y is that X, the number that's there, is equal to Y, the front part of this number, times this power of 10, times 10 to the minus 25. So what I need to figure out is do a calculation, a quick calculation, so that I'm solving this expression for Y. So the thing to do here is multiply the whole thing, both sides, left-hand side and the right-hand side, by 10 times 25. With this, what I'm hoping to get is this will cancel out this 10 to minus 25, and this times X will go on the left-hand side to give me X times 10 to the 25 is equal to Y. So remember that this number here is X. So what I'm going to do is multiply that to 10 to the power of 25 to get me this number that I need to plug in at the front here. So times again, this time it's gonna be 1 times 10 to 25 equals, there it is. Now let me erase those things that are getting in the way. So 0.53008 is that Y. So so just plugging in 0.53, and I don't think I need all those all those other stuff. So so let me just submit with this to kind of make sure that I'm on the right track. Fine, good. So let me finish the other two so that I can finish this question here. Actually, I guess let me not do part C because part B and part C are basically identical with the two different wavelengths. So if I do part B, then using the same method, you should be able to do part C. So for part B, this is the challenge. So you have this relationship here, which gives, where's my color? This relationship here, which gives you the energy of the photon in terms of the frequency. Part B doesn't give you the frequency, it gives you the wavelength. That's why you need a relationship that was under the hint earlier, which tells you that frequency is related to wavelength by speed of light divided by wavelength lambda. Let me just double check. That's how I gave it to you. Yeah, frequency is C over lambda. I don't know. Sometimes I give you the other form and leave it to you to do the algebra. But all right. So I guess one thing I can do is to cut down on some extra work is do a little bit more algebra here to plug this into the expression for photon energy. When you do that, you get photon energy is equal to Planck's constant times speed of light divided by the wavelength. So you can just plug in all your numbers into this one expression. Now, it is a bit of work when you are doing this on a calculator. So if you want to use Wolfram alpha and do it in an easier way, that's fine, not a problem. But let me just do a little more calculator exercise here. So I have 6.626 times 10 to the power of minus 34. So that times speed of light, which is under hint. I mean, I don't actually need that 2.998. Let me just use 3. That's going to make things easier. 3 times 10 to the power of 8 divided by, and the 570 nano Nano is the prefix meaning 10 to the power of -9 or a billion. So let me do that. 570 times 10 to the power of -9 meters. So equals, all of that is that. And this time. Now, I don't want to plug in 3.49 times 10 to the -19 joule because I'm only entering this head number here without the times 10 to -18. Now, you see that this power isn't the same as 10 to -18. So what I need to do is the same thing as before. I need to multiply by something that will cancel out, 10 to -18. So what I do is times 1 times 10 to 18. When that's multiplied to 10 to -18, that will cancel out, and it will give me just the leading number there. Okay, so that's a 0.3. I think I can actually enter 0.35. There's enough tolerance there. I can actually do 0.35. Submit, and that's the correct answer. For part C, you follow the same procedure. You just use different numbers. So hopefully all that makes sense. Let me go through the rest of these questions here. Question 4 is, so it says, follow this tutorial to calculate the energies involved in a photoelectric effect experiment. And hint says review the section 13.2. And the reason I do that is to have you, one, find this formula for photoelectric effect. And then later on, there's going to be something that relates the kinetic energy, or rather the maximum kinetic energy of the electron to the photon energy, and what we call binding energy or the work function. So read all that, get to that. I happen to remember those, so I'm gonna just use what I remember. So the first expression I need to use is the one relating the photon energy to the photon frequency, or here, because I see that I'm going to need to relate that to wavelength, I'll need to write down, so photon, Planck's constant times frequency, which is going to become equal to h times speed of light divided by the wavelength. This is once again using the relationship between frequency and the wavelength. So, all right. Now, I'm going to use a slightly different value of Planck's constant. I'm going to use this one. The difference between this number and the other one you saw previously is what unit of energy we are using. You can read all about the electron volt unit. I won't do that, except that this is the number I want to use. I think that's everything I need. I have Planck's constant. I remember C, 3 times 10 to the 8 meters per second. And the wavelength is given. Yeah, so let me do all that. So Planck's constant is 4.136 times 10 to the power of -15 times the speed of light, 3 times 10 to the power of 8, divided by the wavelength, which is 360 times 10 to the power of, the prefix for nano is -9, so -9. So having put in all that, equal to the energy of the photon is, pretty simple, 3.45 electron volts. So 3.45 electron volts. Let me do all the submit all at once because I don't know what's going to happen to the image that I deleted. Okay, it says if the binding energy of the photocathode is 2, what is the maximum kinetic energy? This is why I ask you to read the chapter, because if you have read the section, you see that the relationship is very simple. The maximum kinetic energy is photon energy minus the work function. So I had the photon energy, 3.45, subtract the binding energy, I get 1.45, and that should be the correct answer. And it asks, at what value of opposing voltage being applied will no more electrons reach the anode? Now, here's a really interesting and useful thing about electron volt. Did I talk about this already? Maybe not. What an electron volt is, well, I just said electron volt, and that is kind of exactly what it sounds like. It's describing the energy change as the charge of the electron. So let me just write down electron charge times, or rather, one electron charge times 1 volt. Now we ask, all right, for an electron going over some voltage difference, how much electric charge it has? Well, it has charge of 1 electron charge. That's kind of self-consistent description. So when an electron goes over 1 volt voltage difference, it undergoes change of energy of 1 electron volt. So the answer here comes out to be really simple. At an opposing voltage of 1.45 volts, the electrons, as it goes through that voltage difference, it'll lose 1.45 electron volt of energy, which is the maximum kinetic energy it could have. So it won't be able to climb that hill. So that's it. Let me submit this to show that the answers are correct. Yeah, correct answers. Good. Let's move on. 6. All right, I need to plug in numbers here, so let's do that. It says something about the de Broglie hypothesis, and this relationship is probably important. To help you make some number sense for what this means, try below calculations. All right, it sounds like I need the Planck's constant I have, and the momentum to give me the wavelength calculation. All right, let's see. Yeah, review wave nature of matter. And because I need to remember this relationship, the hint is helpfully giving me this giving me this information. That momentum is given by mass times velocity. So hopefully we have mass. Oh wait, do I need to look up electron mass? Yeah, let's look up electron mass. By the way, if you are using Wolfram Alpha, you can just type in electron mass because the thing will look it up for you. Yeah, I need electron, yeah. By the way, we have electron mass in the textbook. If you go down to you can also Google it. That's also another way to get it. Under useful information, it'll list a bunch of constants. And one of the constants is the electron mass. There it is. I'm going to need to know that in the SI units, the 9.11 times 10 to the minus 31 kilograms. So let me write that down. So electron mass is equal to 9.11 times 10 to minus 31 kilogram. And I think that might be it. Yeah. So the wavelength, according to the de Broglie relationship, should be wavelength of anything, any object that has momentum is Planck's constant divided by the momentum of the thing, which we can, using the relationship between momentum and mass and velocity, I can write this down as Planck's constant divided by mass times the velocity. If I keep everything in SI units, I'll get the wavelength in SI units, and then I can work it out from there. So, all right, let's plug in the numbers for part A. So we have the wavelength is equal to Planck's constant, 6 point. Oh wait, there is electron mass. I should have looked harder. 6.626 times 10 to minus 34 joule times second divided by the electron mass times the speed. So 9.11 times 10 to minus 31 kilogram times velocity.
4210 meters per second. And I'm not going to necessarily work out all the units. What I'm just going to hope for is that this is the promise of SI unit system. Then when you use all the correct units, basic SI units, then your final answer should have unit of meters. If it doesn't, then something went horribly wrong. So all right, let's write that down. So, or do that on a calculator. So I have 6.626 times 10 to the power of minus 34 divided by, and I could do parenthesis thing, but let me just divide both numbers. 9.11 times the 10 to the power of minus 31. By the way, be careful with something like this. If you are literally typing in times 10 to minus 31, you should probably put parentheses. It's about the whole order of operation. So always double check your final answer makes sense. Divided by this number, 4210 meters per second. 4210. Let's see what we get. We get a super small number. So let me write this down here. The number we get is 1.728. 728 times 10 to the minus 7 meters. Now you can't just plug in this number because it's not asking for the answer in meters. It's asking for answer in nanometers. This is where it's helpful to remember that 1 nanometer is equal to 10 to the minus 9 meters, or to flip the other way around, 1 meter is equal to 10 to the 9 nanometers. So I can basically plug this in for the implied 1 meter here. When I do, I'm gonna get my answer in the units of nanometers. So let's do that. I have that number there multiplied by 1 times power of 9. All right, so that's equal to 170, let's say 173 nanometers. All right, that's interesting. Oh, it says it corresponds to the thermal speed of an electron that has been cooled down to about 1 Kelvin. All right. Let's see. Do I want to do those other numbers? I don't think I need to do those other parts B and C. So assuming I got part A correctly, all you need to do in part B and C is just change the number for speed from 4,210 meters to some larger numbers. And what I hope you will see is that the wavelength gets actually very, very much shorter. So, yeah. Wait, then should I? Yeah, I think you can just plug in those numbers in a non-scientific notation if you want. Or you could use scientific notation, and I'll get to that maybe later. So submit. Good, 173 nanometers is the wavelength of an electron, frankly moving very slow. All right, let's keep going. I think it's exactly the same calculation as the one before. I wish I hadn't erased all those formulas because I could have just reused them. So let me do this correctly. De Broglie relationship is wavelength is equal to Planck's constant over momentum. And since we are being given masses and the speeds, really momentum should be re-expressed using this relationship. Mass times velocity, that the momentum is, the de Broglie wavelength is Planck's constant divided by mass times the velocity of the particle. All right. So each of the questions kind of gives you the mass you are using and the velocity you are using. So let me just pick the most ridiculous example possible and use the one with Earth. So, if we now learn about Planck's de Broglie wavelength and we want to figure out what is the wavelength of the Earth, let's plug in those numbers and see. So my wavelength is equal to Planck's constant divided by mass times the velocity of the object whose de Broglie wavelength I'm measuring. I think I have all the numbers, so let me just plug in stuff. Calculator. So Planck's constant, that is 6.626 times 10 to the power of minus 34 divided by mass of the Earth. It's very high, 6.0 times 10 to the power of 24 kilograms, divided once again by the speed of the Earth around the Earth, 29,800 meters per second. It's pretty fast. All right, all of that is equal to 3.71 times 10 to the minus 63. All right, let me plug in that number. Now, one thing that I hope you will notice before you fail too many times is, yeah, many of these numbers are absurdly small, which is why I'm not even bothering with the power of 10 here. And you should enter the powers of 10 using this notation here. This is what we call E notation. You start out with a leading number, and this single letter says that, oh, what follows is the power of 10. So I have this here, 3.71 times 10 to the power of minus 63. So let me just type that in. I guess if you're starting from calculator, it suspiciously looks like what's already on your calculator. So, it suspiciously looks like that. By the way, lowercase e sometimes works, but get into the habit of getting uppercase e for this. That's what everyone uses. So the de Broglie wavelength is, 3.71 times 10 to the power of minus 63. This is a ridiculously small number. There's a lot of people think that this is smaller than fundamentally measurable distance. So let me just leave that there. Moving on, question 12. All right, that's more calculation. It says, according to the Bohr model, the allowed energy levels where blah. Using this model, we'll calculate one of the possible wavelengths in the line spectrum of the hydrogen atom. Follow the directions below. When necessary, use this value of Planck's constant in the electron volt unit. For some reason, I guess that must be more convenient. And speed of light, this number, but I'll use it 3 times 10 to the 8. That usually is close enough. Let me look at the hint. Do I give any more hint? Oh, I do, yeah. You should read the textbook. I mean, it's always a good idea to at least skim the textbook sections. And here, if you read through it, some benefits you will get is, I don't know if you necessarily need this, but be aware that there's a formula there. And you have this representation of the spectrum, which is good to have in your head. And I think this is what I want you to look at, the transitions from one level to another level. That's a useful thing to be aware of. Here's the whole series of transitions. What we call Lyman series, Balmer series, Paschen series, and actually only the Balmer only, I think it might be only. Balmer series is the one within the visible range. Lyman series, the energy difference is so much that you get into ultraviolet. I think a Paschen series is where it's small enough energy that the wavelengths are long enough that you get into a non-visible range, more like infrared. Skim this chapter and read all this. It's all useful thing to know. Let's look back here and see what I need to do. It starts out with suppose that the electron jumps from a given energy level down to another energy level. So what you're going to need is this formula here. I mean, there are other formulas too, but oh wow, it's not in the summary. There are other formulas too, but the other formulas are a bit more cumbersome to use. Formula that you need is this one. Sorry, this I should have highlighted this better. It's the orbital energy, which is easier for you to figure out. Yeah, I need to reorganize this. I mean, you could use this formula here, but the thing that'll make it difficult is, you have to convert the wavelength relationship to energy. So, so let me write this down as the one that'll make things easiest for you. The orbital energy formula, which is this one. And I recommend that you just use this one, 13.6 electron volts. I mean, there's all these things, but plugging the numbers there, it's a lot of unnecessary work. What's useful for you is that the energy levels of the electron is given by this. So, yeah, that might be something I should have fixed. So let me write it down here. Energy levels of the electron characterized by the quantum number n is minus 13.6 electron volts over n squared. So when it says that electron jumps from one level down to another level, what you need to know are the values of those two energy levels. So let me just do that calculation on a calculator here. So I can do that for the energy level n equals 4. Let me just plug in the numbers there. Minus sign, I'm just going to write it down later. So 13.6 divided by level 4 squared. 4 to the 4 squared. All right, equals 0.85. All right, let me write that down. E4 is equal to minus 0.85 electron volts. All right, seems reasonable. Let's keep going. Energy level E2. So I need to do this calculation again. 13.6 divided by energy level 2 squared is equal to 3.4. Don't forget the minus sign. It's minus 3.4 electron volts. All right. So as you look at these two numbers, what I hope you realize is that because of this minus sign here, the greater number means actually a lower value because it's more negative. So the n equals 4 energy level is higher than n equals 2 energy level. It's less negative. So, I hope all of that makes sense. So when a photon goes from this energy level to here, it's losing energy. And the amount of energy that it's losing, you can calculate it here. It's basically the difference between these two numbers. Let me do this as 3.4, I already had that, minus 0.85. So 2.55. So that's it. Hopefully that's correct. 2.55. Electron loses that much energy. All right, let's see. Let me submit it and see if I get the correct answer there. Submit. Oh, good. All right, let's keep going. So it says, so you need in a question like this, I do highly recommend that you do earlier part first, because you need an earlier part to get the answers to the later part, because the part B relates to energy lost by the electron, which goes into the photon energy which is where now you remember, oh, photon energy of a photon is given by Planck constant times frequency. So you use the Planck constant, which is given here, and I gave it to you in the electron volt units because I kind of figured you'll be answering in electron volt units. So you can solve this for frequency of the photon. So you might need to do a little bit of an algebra here, divide both sides by Planck constant, then you get the frequency of the photon. Frequency of the photon is equal to the energy of the photon that we have from earlier calculation, divided by the Planck constant, h. So let's plug in the numbers. We have I already have 2.55 in electron volt units, divided by the Planck constant in electron volt units, 4.136 times 10 to the power of minus 15 is equal to, darn, that's a super large number. You know what, so you could use scientific notation, and if that's how your calculator gave it to you, great, use that please. Here, I just have all these digits, so I'm just gonna plug that in. Let me push that off to the side so that I can look at it. So I'm gonna have 616, 537, 717, 601, 547, and then it's 0.38, whatever, 39. Now, obviously, this is not really all that recommended, but this does give you the right answer. And if you want to convert that to scientific notation, great, good job. But just entering it that way is fine. Converting a large number like that into scientific notation is not a skill I'll be testing you on an exam, so you don't really need to practice that. All right, part C. Given the answers to A and B above, so I'm just working down each question, because in part C, now I need to know the answer to part B. So I'm being asked for the wavelength of the photon. This is where hopefully you'll remember the relationship between frequency and wavelength. You have this relationship that wave speed, or the speed of light, is equal to frequency of the light times the wavelength of the light. Or solving that for wavelength, wavelength is equal to speed of the light divided by the frequency of the light. So yeah, I need to just plug in the numbers. I have the speed of the light here. I have my frequency of the light here, which I also have there. So let's just plug in the numbers. I have 2.998 times 10 to the power of 8 divided by, let me just type in all that, 616, 5377, 1760, 1547.39. I don't actually have to enter that many, but let me just do that. It's easier, oddly enough. All right. Then I get this number here. This is where I do have to be careful. I'm asked for answer in the units of nanometers. This is where you do need to remember that 1 nanometer is equal to 10 to the power of minus 9 meters, or 1 meter is equal to, multiplying both sides by 10 to the 9, I get 10 to the 9 nanometers. Or another way to put it is there's 10 to the 9 nanometers in 1 meter. So on this calculator, what I need to do is, this is in meters. So that's So I'm replacing 1 meter with a 10 to the 9 nanometers. So let me do that. Times 1 times 10 to the 9 nanometers. So, okay, 486 nanometers. Yeah, 486. Submit. Good. So this is all done. Good. So this is chapter 13. I think the remaining 2 questions are not calculation questions. Yeah, so you can do that on your own.